Assalamu alaikum wa rahmatullahi wa barakatuh, and a very good afternoon to all viewers. It is a great pleasure to welcome all viewers to the 16th series of Research and Innovation webinar, School of Electrical Engineering. My name is Sherry, the moderator for today's session. This program is brought to you live from School of Electrical Engineering, Faculty of Engineering, University Technology Malaysia's Facebook. Without further ado, I would like to invite Professor Dr. Muhammad Kamal Ibrahim, the Associate Chair of Research and Academic Staff, to give a short opening, as well as introduce our guest speaker, IR Dr. Michael Tan Lung Peng, the Head of Computational Nanoelectronics Research Group. Over to you, Prof.
Okay, thank you very much, Puan Sherry Huzaima, for introducing this event. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And salam sejahtera to all viewers. Thank you once again to all viewers that follow this webinar through our FB Live School of Electrical Engineering. My name is Professor Muhammad Kamal Abdul Rahim, and I am a Chair of Research and Academic Staff, School of Electrical Engineering, Faculty of Engineering, University Technology Malaysia. Our topics today entitled Recent Advances in Nanoelectronics that will be given by Head of Computational Nanoelectronics, short form of CONE, Research Group IR Dr. Michael Tan Lu Peng. Before he gives his webinar, I would like to introduce our speakers to this. And don't forget to share, like, and comment at our FB Live School of Electrical Engineering, University Technology Malaysia. Dr. Michael Tan obtained his Bachelor of Electronic Engineering at University Technology Malaysia and was appointed as a tutor in 2003. He started his master by research on 2004 and carried out his research as a graduate intern in Penang Design Center or PDC, Intel Technologies Grand Berhad. He was awarded Masters of Engineering from University Technology Malaysia in 2006. Subsequently, Michael was awarded his PhD degree in July 2011 at the University of Cambridge, United Kingdom. Presently, he is a senior lecturer and head of Computational Electronics Research Group. In addition, he is a professional engineer with practicing certificate with BEM, professional technologist with MBOT, and chartered engineer registered under the Engineering Council, United Kingdom. He is also a life member of the American Physical Society. His research interests are in device modeling and circuit simulations of quasi-low dimensional nano transistors. Now, the webinar starts with a brief introduction to Computational Nanoelectronic Research Group. Then the talk moves on to higher research in nanoelectronics, particularly on the downscaling of transistor, imaging materials, and the application and nanoelectronics. Without further ado, I would like to invite IR Dr. Michael Tan Lu Peng, Head of Computational Nanoelectronics, or the short form of CONE Research Group, to give his webinar on the title Recent Advances in Nanoelectronics. Over to you, Dr. Michael Tan.
Good afternoon, everyone. Thank you, Prof. Kamal, the Associate Chair of Research and Academic Staff, School of Electrical Engineering. And also thank you, Puan Sherry, the moderator for this webinar. I'm Michael, the Head of CONE, and I'll begin a brief introduction of our research group. Our group carry out various types of research and advanced simulation, analysis, design, modeling, and simulations of advanced material. We normally investigate silicon and carbon-based material. We also do analog CMOS circuit design, biomolecular sensing, graphene sensor, zinc oxide, nanowire. Our activity also comprises TCAD simulation, fabrication, and characterizations of various sensing and memory application, and digital circuit simulation using HSPICE. Right here are the research members of our group. This cone research group was founded by Professor Razali Ismail. And then now I am the present head of cone. And we also have Dr. Suhaila, Dr. Yusmiras, Dr. Suhana, Dr. Nuro Izaila, Dr. Zahara, and Dr. Afiq. So now let's look at our research profile of each of the group member. So for Dr. Yusmiras, her research interest is in advanced material-based device and sensor fabrication. She also does analog and mixed signal microelectronic circuit, bio CMOS co-design, and point-of-care devices. Next, we have Dr. Suhaila Ishak. Dr. Suhaila research interest is in photonics, and also she's an expert in Verilog and VHDL implementation. She also does low power amplifier design, Geiger mode avalanche photodiode design and fabrication, electrical and optical experiment setup and categorization for biosensing application. Currently, she has 1 PhD student and 4 master students. Next, we have Dr. Nuro Izaila. Dr. Nuro Izaila has obtained a PhD from the prestigious University of Tokyo. Her research interest is in semiconductor device engineering. She also did TCAD simulation and analysis. This is one of the lab subjects that we offer on TCAD simulation. She also does design technique and FET-based memory application. And she does a lot of variability and reliability tests issued in nanoscale FET devices and also reliability physics of nano electronic devices. She has 1 master student and 3 PhD candidates, 2 master students and 2 PhD candidates so far. And she has Matangi, our international student from India. Next, we have Dr. Zahara. Her research interest in semiconductor device fabrication and characterization. She categorized nanomaterials and semiconductor devices, particularly on carbon nanotube and graphene nanoribbon. She has 1 master student at the moment, Muhammad Faizal. And we have Dr. Suhana. Dr. Suhana just completed her CEO at Faculty 2.0 at Nano Malaysia Berhad. She does a lot of fabrication and characterization of semiconductor devices, particularly on zinc oxide, thin film resistor, diode, nanowire for sensing application. She also did for carbon nanotube-based electrode for gas sensing and healthcare application, nano electromechanical sensor, device of experimental or process optimization, and also TCAD simulation. She has 3 PhD students and 1 master student. Next, we move on to Dr. Afiq. So Dr. Afiq is an expert in SPICE modeling, semiconductor devices, particularly on graphene-based devices, multi-gate FET, nanowire junctionless nanowire transistor, which is on his PhD, numerical TCAD simulation as well, which include characterization, optimization, tunnel barrier engineering, and reliability. He also do DC and CV characterization of MOSFET and MOSFET parameter extraction. Currently, he has an ongoing project grant on interface trap density of junctionless nanowire transistor, where he has to do extraction and compact modeling, and as well as charge-based modeling and gate all around floating gate. So right now, Dr. Afiq is looking for master student. He has this topic called optimization and compact modeling of multi-bridge channel FET, MBC FET for logic performance CMOS circuit. In this talk later on, I'll explain more on multi-bridge channel FET. So those who are interested, you can contact Dr. Afiq, which is his email is given here, and mafiq@utm.my. Okay, next is about me. My research interest is on semiconductor material engineering. So what I do is I do modeling on 3D, 2D, and 1D carrier transport in nanostructure. We work on silicon and carbon base, as well as transition metal dichalcogenides, monolayer devices. In the previous, we do digital simulation, logic simulation using HSPICE. And at the moment, we are doing nearest neighbor type binding simulation. I have Alvin. He just completed his master. He now doing his correction. We have Ching Hui Chan, PhD candidate, which is who is working on drift career, and Moven is working on his silicon. Nicholas Leong is a PhD candidate working on interface trap charges in MOS2 devices, and also Ken Long working on graphene nanoribbon. He just submitted his thesis and waiting for Viva at the moment. All right, so now let's look at our first topic here is on nanotechnology. So what is actually nanotechnology? Nanotechnology is understanding and control of matter at nanoscale, and usually is a range between 1 to 100 nanometer, and it encompasses nanoscale science, engineering, and technology. It involves imaging, measuring, modeling. You see, this is a keyword here, modeling, and manipulating matter at this length scale. So by working in nanoscale dimension, we hope to create tools and products that address the challenges that we are facing in the world right now. So with nanotechnology, we can get smaller, faster, and more portable electronic devices with large data capacity. We can produce medical devices and drugs to detect and treat diseases effectively, and also hope to minimize the side effect. We can create low-cost filter to provide clean drinking water. We can make stronger, lighter, and more durable material, and we can have sensors that can detect harmful chemical. How big is a nano? A nano size is a billionth of a meter. So let's just find how tiny that is actually is below. If you look at nano size, 1 nanometer is actually a sugar molecule. And when we work on 1 to 100, we usually work at the size between the sugar molecule up to a virus. All right, so this is how small it is. So nanotechnology, we learn about the beginning of science and studying the extremely small and its fundamental concept. And if you want to talk about nanotechnology, we have to find out who are the 3 champions of nanotechnology. They are Feynman, Taniguchi, and Drexler. So let's begin with Feynman here. So Richard Feynman is a Nobel laureate in 1965. And in 1959, he gave this a popular talk here, which entitled "There's Plenty of Room at the Bottom." So his idea was on the ability to manipulate matters on an atomic scale. So in the future, he predicted that we can make nanoscale machine that can arrange the atom we want and do chemical synthesis by mechanical manipulation. He also presented the possibility of swallowing the doctor as a concept involving building a tiny swallowable surgical robot. So in 1959, as a thought experiment, he proposed that maybe in the future we can develop a set of tiny manipulator hands connected to the operator hand, and we can build small scale machine tools. And the small tools can then build and operate smaller hands and tools and so forth, and a billion tiny factory to achieve a massively parallel operation. So with the invention of scanning tunneling microscope in 1981, and the discovery of fullerenes in 1985 led to the emergence of nanotechnology. So the term nanotechnology has been coined by the Tokyo University of Science professor Norio Taniguchi in 1974 to describe the precision manufacture of material with nanometer tolerance. So his definition of nanotechnology then is processing, separation, consolidation, and deformation of material by one atom or one molecule. Then we have Eric Drexler. So Eric Drexler used the term nanotechnology in his 1986 book, Engine of Creation, the Coming Era of Nanotechnology, to describe what later known as a molecular nanotechnology. So in that book, he proposed the idea of nanoscale assembler, which will be able to build a copy of itself and other items of arbitrary complexity. So the difference, the idea between Drexler and Feynman is that his concept was a billion tiny factory, and he added this idea that they could make more copy of themselves using computer control instead of using human operator in his book. So now let's look at scaling. All right, so planar field effect transistor. So a transistor is a semiconductor device that is used in amplifier or electronically controlled switches. So transistors are basic building blocks that control an operation of a computer, mobile phones, and all other modern electronic circuit. So you see that field effect transistor here is a 3-terminal electronic devices. They have gate voltage, they have source and drain. The on-off is achieved by changing the conductivity between the drain and the source terminal. At the same time, the transistor is also is a basic unit of the CPU. Transistor can be packaged independently or in a small area. Integrated circuit can accommodate 100 millions or more transistor. So let's look at the scaling here. So by scaling, we usually look at Moore's law, and usually most of the time people say that Moore's law is nearing its end as the transistors are scaled down to sub 10 nano regime, where the features tends down to a few atom per devices. So by using this Moore's law, we are able to increase the number of transistors on a chip every 18 to 24 months. And this has powered the mainstream microelectronic for the past decade. So the key of successive scaling in MOSFET, you can see that in the beginning, when they scale, the nominal feature size and the gate length are the same. But getting now to the earliest 2000s, we see that the gate length sometimes are below than the nominal feature gate. The evolution in microprocessor also allows Intel, they have just developed their latest 11th generation Intel Core processor called Tiger Lake, manufacturing using Intel 3rd generation 10 nanometer process node called 10 nanometer super fin. So the motivation behind this emerging device is due to scaling issue. So when we scale down, we have this effect called short channel effect that causes high leakage current. We have this term called drain-induced barrier lowering, threshold roll-off, velocity saturation effect, and also quantum mechanical effect. So these effects degrades the device performance and also reduce the accuracy of a classical model. So what are the alternative emerging devices for conventional MOSFET? The alternatives are we can use new material, or we can proceed with new structure, or a combination of both. For example, if a new material that we are doing right now in research, mostly during my PhD, we work on carbon nanotube, graphene. Right now, we are moving on silicene, germanium, transition metal, new structure, all right? Instead of planar MOSFET, we are going for vertical MOSFET. We have FinFET, multiple gate all around, silicon nanowire, or a combination of both. So who is responsible to determine the research direction and improvement of semiconductor field? All right, so our semiconductor industry have benefited from the roadmap guidance since the mid-80s. So we have this called this NTRS, which is the National Technology Roadmap for Semiconductor. And we also have the ITRS, which is the International Technology Roadmap for Semiconductor. So the roadmap outline the main needs of the semiconductor industry for years to come, and also identify future challenges and possible solutions. So making transistors smaller by means of advanced lithographic technology enable both increased integration levels and improve IC performance. So the NTRS and ITRS, they uses a bottom-up approach as standard microprocessor and memory, where they will introduce a very quick pace, barely allowing time for the system house to integrate them in the product. So system integrator was having a problem because they could not keep up with the rates at which new memories and new processor products were introduced. Since the industry changed in the 90s from 3 to 4 year cycle to a 2 years technology cycle. So then in 1998, ITRS provided the vision that initiated research, development, and manufacturing communities to develop a completely new transistor structure. So ITRS was produced annually by a team of semiconductor industry experts from Europe, Japan, Korea, Taiwan, and the USA between 1998 and 2015. So ITRS provided main reference for university, consortia, and industry researchers to stimulate innovation in various areas of technology. Now we come on to IRDs. So IRDS is called International Roadmap for Devices and System. So the arrival of foundries and fabless company transformed the electronic industry into a top-down driven industry for the past 15 years. So the ITRS adjusted to this new ecosystem and transformed into the International Roadmap for Devices and Systems sponsored by IEEE. So IRDS now is addressing and the requirements and need for the renewed electronic industry. It is predicted that in the next 10 years, the ability to lay out IC in a 2D grid will reach a fundamental physical limit. As a result, they are now converting from 2D to 3D architecture for integrated circuit, which are vital for the continuity of increasing transistor count and improving performance. In IRDS as well, there are more groups, and these more groups in IRDS, their goal is to identify key technical requirements and challenges that are important to prolong the historical scaling of a CMOS technology. The group provide physical, electrical, and reliability requirement for logic and memory technology. There is also another group called Emerging Research Material Group. And in this group, they identify emerging material such as germanium nanowires, carbon nanotubes, other 2D material. And also, if you look here, they also identify 2D material as an emerging material for transistor scaling. Why they use 2D material? Because they are high in mobility and also they provide good channel control. So why do we want to do modeling and simulation? Modeling provides new insight into the operation of modern semiconductor devices and explore new phenomena of device physics. So in simulation that we normally use are Centaurus, Silvaco, QuantumWise. For my student, we also use MATLAB. We also reduce the development cost and time that allow user to examine various physical aspects. So this is important as it allows for performance enhancement without the need of monetary investment to obtain new specialized equipment. So the device modeling methodology that we do, we normally start with modeling the materials and we do an electronic property simulation to obtain the electrical property of the material. Then once we get the electronic property, we can move on to the device and we do a device simulation. You can use HSpice to do that and a lot of the simulation tool that explained before that. So device simulation is important because it provides guidance and explanation for measurement and result from fabricated devices. Now let's look at FinFET. FinFET, which is known as Fin Field Effect Transistor, is a type of non-planar 3D transistor used in the design of a modern processor. So if you look at the figure here, FinFET is around between 10 to 15 nanometer. We have FinFET right now. So let's look at this technology node here. It is known that before the mid-90s, the logic technology nodes were synonym with the gate length. Right? If you see the earlier on here, when it's a 500 nanometer node, you get 500 gate length. Then as it progresses, actual gate length shrunk faster for a while, and then they stopped shrinking. All right, now they stopped shrinking. You can see that. So let's see, for example, here in 2001, all right, when Intel switched to FinFET at 22 nanometer node, the devices has 26 nanometer gate length, 40 nano half pinch, and 8 nanometer wide fin. So you can see here that the industry node number 22 nanometer had absolutely no meaning because it has nothing to do with any dimension you can find on the chip dial that related to what you are really doing, right? You are doing 22 nanometer, but you're getting 26, 40, and 8. So because of this, Gagini, who is the chairman of IEEE, International Roadmap for Devices and System, proposed that the industry adopt a 3-number matrix, all right, that combines contacted gate pitch, metal pitch, and the number of layer on devices on the chip. All right, he proposed that we can use this structure of matrix. We have G48, M30, and T1 here. So let's look what are all these here. So if you look at this figure here, the gate pitch is something to show here, the gate pitch here, and we have the gate length and the metal pitch. So the aim of the scaling is that we want to reduce the track height and cell size in a standard cell layout at each node. So for example, if you look at 7 nanometer, all right, 7 nanometer is define the height of a standard cell layout. 7 nanometer might have 6 track of height cell for device with a gate pinch of 56 nanometer. and a metal pitch of 36 nanometer. And this is more accurate than using the technology itself. So Intel introduces FinFET in 2011, where now it grows in the third dimension. So we used to have planar, and now we have a lot of CPU, iCore 7, iCore 5, iCore 3 that you use are based on FinFET. And for the future, Intel also introduced this nano ribbon, the future gate-all-around FET transistor that takes the idea of a FinFET but to the next level and provide true 3D, hence the gate-all-around coverage of the transistor channel. So you can place a fin inside the door that have 3 or 4 sides to cover, but while GAA FET, gate-all-around FET, have all side cover. So this is the advantage of using the nano ribbon GAA FET. So Intel is expected to introduce the gate-all-around FET at its 5 nanometer process in 2023, perhaps followed by the stacked PMOS and NMOS devices at 3 nanometer in 2026. I have prepared a video for you, so let's look at it later on after this. So FinFET is changing to nano wire and nano ribbon now. All right, how are they doing? We can also, how they are doing it, Samsung is also following up as well. So Samsung are also using this called multi-bridge channel FET, which is the topic that Dr. Afiq is doing right now. He's looking for master student. This is the one, multi-bridge channel FET. The innovation beyond FinFET. Samsung has already reviewed their own GAA FET, a different name than Intel. They're using multi-bridge channel FET or MBC FET design, which are due to enter reach production by 2020 this year. And let's look at this multi-bridge channel FET.
Whenever semiconductor technology faced challenges, there has been a guiding light to help navigate the maze. Evolution of transistors is a major component of technology development. Planar transistors have been used for generations, with voltage scaling to save power. However, short channel effect ultimately limited usability. FinFETs were the solution and made further voltage scaling possible. Unfortunately, limitations are faced again. For ideal electrostatics, the channel needs to be fully surrounded by the gate. This is known as gate-all-around. Typical GAAs are nanowires. However, integration complexities of nanowires outweigh the benefits. This led Samsung Foundry to create a unique version of GAA with all the advantages but minimal complications. Samsung Foundry proudly introduces our multi-bridge channel FETs. MBC FETs consist of multi-stacked nanosheets. One advantage of MBC FETs is that additional area is not required to improve speed. FinFETs need fins to be laterally added, while nanosheets can be vertically stacked. MBC FETs are compatible with FinFET designs. Designers can replace FinFETs with MBC FETs without changing the footprint. Performance can also be improved without area increase. MBC FETs are the most advanced technology that provides solutions from low power to high performance applications, including AI, autonomous driving, 5G, and high performance computing. With MBC FETs, Samsung Foundry will be the guiding light for the future of the semiconductor industry. Samsung Foundry.
All right. So the advantages of using MBC FET is that they mentioned just now in the video that additional area is not required to improve speed because you can stack it vertically. And the good thing is it's compatible with the traditional FinFET design and compatible with the existing processors. All right. So Samsung is planning to introduce the nanosheet GAA FET on its 3 nanometer design, replacing FinFET entirely. They also provided this MBC FET PDK version 0.1, a process design kit, which is a set of files used within the semiconductor industry to model fabrication process for the design tools used to design integrated circuit. And Samsung PDK includes SPICE, DRC, design rule check, layout versus schematic, parasitic experimental test, P-Cell, Field Deck, PNR, Tech File, EDA partner include Cadence, Mentographic, and also Synopsys. Okay, now we move on the quasi-low dimensional structure, which is based on my research area. So first of all, when we talk about material, we have a classification of nanoscale dimension. So when we talk about 3D, we say that you can say that there's no dimension in the nanoscale regime or scale. And then we move on to 2D material, which means that two dimensions are in macro scale, one in nanoscale. And there are also 1D, 2 dimension in nanoscale, 1 dimension in macro scale, and 0D, where all dimensions are at the nanoscale. So 2-dimensional material has great potential for future electronic devices due to the stability and atomically thin structure. So most of the research, if you read right now papers, we are working on 2D material because they have astounding physical and chemical property in contrast to the 3D bulk counterpart. So what kind of 2D material that you can look for? One of it is called transistor metal dichalcogenides, which is one of my PhD student, Nicholas, is working on, TMDC. All right, they consist of a hexagonal layer of metal atom. All right, the atom is sandwiched between 2 layers of chalcogen, and they use the notation MX2. So they have band gaps with advantages with semiconductor property, good flexibility, and high transparency. Molybdenum disulfide is a member of the TMD family and widely studied due to these advantages. So we also have carbon-based material. Early on, when we talk about fullerenes, this is fullerene shown here. And we have carbon nanotube, which I work on during my PhD, working on graphene. And also when we get smaller, we have graphene nano ribbon. Okay. So we also have this material called silicene. Silicene is a material consists of silicon atom, all right, arranged in a honeycomb structure, just like graphene, possessing a direct cone and zero gap in the band structure. So you can also go for silicene germanium. Silicon and germanium are graphene cousin, considered to be single layer of sp2 hybridized silicon and germanium forming a 2D honeycomb lattices. So these are all the research modelings that we are doing right now. We are studying silicene, compare the performance with graphene, germanium. And also another material that is quite popular and in many devices right now is called gallium nitride. Okay, gallium nitride has a wider band gap than silicon. It can sustain higher voltage than silicon. So most of the charger, the handphone charger right now, they are adopting and they are changing to gallium nitride. Okay, companies like Anker, okay, they're creating this power adapter here. Though gallium nitride is more expensive than silicon right now, gallium nitride charger require less component than silicon charger, which makes their prices competitive. There are also research paper demonstrate how to grow gallium arsenide, gallium nitride on silicon. They found that you can use graphene as an intermediate layer. Companies also hope to use gallium nitride material in components including portable batteries. So what are the applications in nanoelectronics that we can look for? All right, I prepared a video for you. And this video, they've shown that by using nanoporous graphene in smart filter and sensor. Okay, if you want to read more about this, there's a DOI here, you can see. Okay, now we proceed with the video. So the word nanoporous here, which means that it's a small gap, it's a small hole that you can use for detection and sensor. See this wide gap here. So they're building the nanoporous right now, and these are the potential application that you can use. Electrical sequencing of DNA. They can detect the DNA, A, G, T. Also selective filtering and sensing. Okay. And portable dialysis with implanted device. Alright, to know more about this, you can read this paper here, Bottom-up synthesis of multifunctional nanoporous graphene. Okay, so what are else other application? You can also use graphene-based standalone solar cell, solar energy converter for water desalination and purification. Desalination is a process which removes excess salt and mineral from water, or the chemical processing of changing seawater into potable water. This author Young demonstrated a standalone solar cell. See, now you have solar cell, and you use solar cell converter using honeycomb graphene for material, and you can also convert sunlight into heat, and you also can do desalination process. So many things you can do with it. Distill water from various water sources into steam and produce purified water with high efficiency. There are also a company in Canada that are working on graphene sensor for COVID-19 rapid test. So now instead of using the nasal swab, with a long swab here, you can use the saliva test. All right. They're now currently working on it. Graphene Leader Canada. And companies like Qualcomm, okay, Qualcomm, usually the chip that you use in your smartphone right now, are also using TSMC 7 nanometer FinFET that we explained earlier on. And in this Snapdragon 865 is a high performance 64-bit ARM system on a chip designed by Qualcomm, introduced in the late 2019. If you are using this handphone right now, they are most likely you are using flagship phone are using Cairo 585, which they have 8 cores. You can see here they have some cores running on 1.8 gigahertz, 3 high performance Go Cairo 585 operating at 2.42 gigahertz, and also 1 prime Cairo Go operating at 2.84 gigahertz. All right, and the size of the Snapdragon 865 is actually less than a coin. So right now, we also, Qualcomm is also coming out with this quick charge technology. So remember the time that when you are using old smartphone, micro USB, it takes a few hours to charge your handphone. And this is the phone that I'm using right now, Samsung. They are using, they can support 25 watt and 45 watt fast charging. But now there are a new contender to that, all right? The new contender, they are called Qualcomm Quick Charge 5. All right, just was recently announced in July 27, a few months ago, up to 100 watt of power and on a mobile phone with 4,500 milliampere battery. Qualcomm promised 50% in just 5 minutes of charging. So is that possible? Yes, it is. If you look at this, the new Xiaomi 10 Ultra, it's the first phone with the Qualcomm 500 watt quick charge 5 technology, where they can say the phone can provide 120 watt charge, and within 5 minutes you can get 41% charge, and less than half an hour you can get 100% charge. All right, so these are all the applications by using Nano Technology, FinFET, we are able to get all this right now. And to provide that, you also need a charger, right? So the charger that I mentioned earlier on, gallium nitride, companies are right now coming out with all this gallium nitride. They call GaN fast charger, all right? GaN fast charger that upgraded from a silicon predecessor, 2.5 fast charging. And not only that, you can use this GaN charger. They can charge your laptop. Right now, I've seen in Kickstarter, they have 200 watt GaN charger. All right, can charge 2 laptops and also your mobile phone. All right, so these are the wonderful technology. So to recap all this, just want to bring you up to our publication from our group here. So far we have 184 paper published in Web of Science. Then we have a lot of conference paper as well, and proceeding book. And also would like to thank Prof. Razali, because Prof. Razali, the former head of group of Cone, he helped us a lot with a lot of Q1 and Q2 publication. All right. So right now we are working now to publish more paper. And just to share with you my experience of publishing paper, this is one of my PhD student. So this paper is on 2-dimensional modeling of silicon. Yeah. With aluminium as electronic property. You can see here that we submitted the paper in 2019 on 5th of May here. Then after that, because the process was quite long at that time, we retract the paper, withdraw with the paper, and we submitted to other journals. And the experience is that some of the paper, the editor did not accept it because they say that they asked us to submit to another journal, and we have a lot of rejection through the way as well. So you can see here we try number 2, number 3, 4, 5, 6, 7, 8, a lot of rejection, correction. And in the end, in early 2000, we submitted again in Advances Nano Research, the same paper as the first one. And it submitted in 2020, was revised in July, and it was accepted recently in July 2020. And this was a Q2 paper. So through our experience is that as a researcher, you always have a hurdle along the way. So just advice for a lot of master or PhD student who are writing the paper, if you get rejection, it is normal. All right. See, look at us. My PhD student have to endorse so many rejection until in the end we get our published in the end. All right. If you have any question, we can proceed back to Prof. Kamal. And if you want to contact us, you can contact me at michael@utm.my. Especially, we also are currently looking for many master and PhD students to work on this computational nanoelectronics. All right. With that, I'll send this back to Prof. Kamal.
Okay, again, I would like to take this opportunity to thank you to Dr. Michael Tan for sharing a very informative session. Now I would like to open for any Q&A session to all viewers. You can post your question to the Facebook comment. Okay, while we are waiting for a question, so maybe I have a question to Dr. Michael. Okay, what is the advantages of using graphene compared to silicon, and do you think that graphene will replace silicon in the future?
All right. So why we want to work on graphene is that because graphene has they have excellent property, electronic property compared to silicon. They can also overcome the leakages that we face in traditional silicon. So at the current stage, graphene has shown many superior property, especially the one-tick structure with higher mobility. All right, but there are still many challenges to mass produce. Okay, so if you just produce a single graphene sheet in the lab, it's okay, no problem. But challenges are mass production. All right, so how do we do if we can overcome mass production in an efficient way? then graphene can replace silicon in the future. So in my opinion, there are still a lot of work required in order graphene to replace the mature silicon fabrication processes that we have right now.
Okay, thank you. Okay, maybe one more question. Okay, recently the focus has changed from silicon-based transistor to graphene nanoribbons based on transistor, and molding stage is still in early stage. Is there any graphene transistor simulator suggestion?
All right, thank you, Prof. As I know, Nemo and Nano Tickets, which are working on Linux, they are a famous graphene transistor simulator. There are also SPICE compatible model of dual layer bi-layer graphene field effect transistor provided by the Southampton University, and you can also find many simulator graphene on nanohub.org. This is where we normally go to learn more about quantum devices. And our group cone as well, we also have a simulator we call GFATSim, produced by my FYP student. It's a simple graphene field effect transistor which we can simulate the all right. Okay, Prof.
Okay, thank you very much, Dr. Michael. I think that's the end of our Q&A. Okay, with that questions, that is end of our webinar today. So now I would like to pass over to Point Sherry for the closing remarks and introduce our next week webinar series on research and innovation, School of Electrical Engineering, University Technology in Malaysia. Over to you,
Thank you, Prof.
Sherry.
Thank you, Prof. Kamal, and thank you also to our guest speaker, IR Dr. Michael, for sharing a very interesting topic just now. Thank you, Doctor. All right, viewers, we are at the end of our session today. Thank you all for taking out time to watch this live telecast. And for those who missed this live session, can watch the video again in our Facebook. Don't forget to like, comment, and share our Facebook and videos to your friends and colleagues. And please don't forget to join us next week, 6 October 2020, 2:30 p.m. for the next series of webinar with our guest speaker, Associate Professor Dr. Nur Hisham Kamis, the head of Sonar Technology and Marine Instrumentation Research Group, on the title Applications of EDM in Biomedical Engineering and Research Projects in Sonar and Acoustics Engineering. Alright viewers, as usual, I will end this session with a quote. Every situation in life is temporary, so when life is good, make sure you enjoy and receive it fully. And when life is not so good, remember that it will not last forever and better days are on the way. Okay, dolls, keep on smiling. See you all next week. Stay safe, keep your distance, and stay tuned. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.